Hello and welcome to the NPTEL course on thermal management of electronics. I am Parmod Kumar.
And I am Sarthak Nag, and we work at the School of Mechanical and Materials Engineering at the Indian Institute of Technology, Mandi. Thermal management is all around us. Consider our planet Earth. Small disturbances in the global thermal balance can lead to significant consequences such as heat waves, changing weather patterns, and extreme climatic conditions. Similarly, the human body continuously regulates its temperature despite changes in the surrounding environment. Mechanisms such as sweating and blood circulation help maintain a stable body temperature and ensure proper functioning of our organs.
The same principle applies to engineering systems, whether it is a power plant, an automobile engine, a battery pack, or a microelectronic device. Performance and reliability depend strongly on how effectively heat is managed. However, contrary to the natural systems whose thermal management is partially self-regulatory, thermal design is required to ensure the reliable performance of the engineering systems. At the smallest scales, modern electronic systems are becoming increasingly compact, powerful, and energy intensive. From the smartphones and laptops to electric vehicles, power electronics, artificial intelligence hardware, and data centers, managing heat has become one of the most important engineering challenges. Excessive temperatures can reduce performance, accelerate component degradation, and compromise system reliability. Effective thermal management is therefore essential for ensuring the safe, efficient, and reliable operation of electronic systems.
So, in this course, we will begin by building a strong foundation in heat transfer for electronics. We will discuss the heat generation mechanisms in electronic devices, temperature dependent failures, reliability considerations, and the overall thermal design process. We will then cover the fundamental mechanisms of heat transfer, thermal resistant network models, and thermal interface materials, concepts that form the basics of electronic cooling analysis.
Next, we will move to convection and radiation heat transfer, where you will learn about convective heat transfer coefficients, boundary layers, forced and natural convection, radiation heat transfer, and experimental techniques for temperature and flow measurements.
Building upon these fundamentals, we will study practical air cooling solutions used in electronic systems. Topics include the thermal specifications of microelectronics packages, natural convection cooling, forced air cooling, fan selection, heat sinks, their material selection, and flow management in enclosures and racks.
The course then transitions to liquid cooling technologies. We will discuss the need for liquid cooling, coolant selection, cold plates, microchannel heat sinks, pressure drop considerations, pump selection, two-phase cooling such as pool boiling, flow boiling, and immersion cooling technologies. We will also compare single phase and two phase immersion cooling systems and examine their design considerations and practical applications.
The next section will focus on passive two-phase thermal management devices, including the heat pipes, vapor chambers, loop heat pipes, and oscillating heat pipes. We will discuss their operating principles, performance limits, material selection, and engineering applications.
Further, we will explore phase change materials, overview of jet impingement and spray cooling techniques, thermoelectronic cooling, and the trade-offs between passive and active cooling approaches.
Finally, we will then discuss emerging and future technologies in electronics thermal management, such as superfluid microbubble based cooling, microfluidic monolithic cooling systems, thermal management of electric vehicles and data centers, ranging from rack level to chip level architectures.
Throughout the course, we will combine fundamental theory with practical engineering design considerations, numerical examples, and real world applications, enabling you to analyze and design thermally efficient electronic systems.
This course is intended for senior UG students, postgraduate students, researchers, and even practicing engineers from mechanical background, electrical, electronics, materials, and other disciplines.
Whether your interest lies in electronic cooling, power electronics, electric vehicles, data centers, or next generation thermal technologies, this course will equip you with the knowledge and tools required to address modern thermal management challenges. We look forward to having you join us in this exciting learning journey. Thank you and see you in the course.